All right, so the purpose of this video is to go back and just remember what the coefficient of determination is. I know everyone in this class has had this already, so it's going to be a quick rehash, and to estimate what that or is that sigma squared is, the amount of variation that's in sort of in the process itself. So right now, what we've already talked about is estimating the model parameters, and we've been really kind of focusing on that. And this I call this 2, as in, we need to estimate the last model parameter, the sigma squared here. Uh, so we have been concentrating on the beta 0, beta 1 so far. We've done gradient descent. Last video I talked about linear algebra to get beta 0 hat and beta 1 hat using the data. Now what we want to do is we want to use that data in order to find sigma squared. And that's just that random error sort of in the process that our modeling efforts really can't do anything about. And so if you kind of looked at a picture here, or at my 2 pictures, you would see that maybe this one has a sigma squared that's kind of tighter, right? So we would expect, if you kind of look at this data and this were the line that we estimated, we would think that this one was a little bit tighter than maybe this one, right? So that's the idea. Maybe sigma squared is small here, and sigma squared is large here. Now, I make that with a caveat, is large. And what's the caveat? Is that the scales here are the same, right? So the scales on the predictor variables are the same. They mean something. So if this scale were in billions and this was in ones, I don't know if I could still say that, right? Because the difference between this would be billions instead of just, and this would be 1, 2, 3, 4, right? So the idea is that if these scales are the same on these pictures, then we can say things like we expect sigma squared to be small, if the data kind of looks like this and it's around the line, and larger if it's away from the line. Okay, so let's remember what variation is real quick. It's just a measure of how spread out the distribution is. And if we had data and we were going to do it, then so if you had x1, x1, x2, x3, xn, we had n pieces of data here, and we wanted to say something, well, how spread out is this data? Then what we would do is just simply sum the squared distances away from the mean, right? So we're going to use the data to calculate this guy first, and then what we would do is go through each one of those pieces of data and subtract out whatever x bar is. And if you remember back in your statistics class, we divide by n minus 1. We call it the degrees of freedom. And the real reason is we don't know the true mean of the true mu of x, mean of x. So what we do is we use the data one time already to estimate that parameter, and that's why we get n minus 1. There's a reason behind that. It's a little bit more beyond this video right now, but we could talk about that in class if you guys are super interested. Okay. So that's just a recall what that sucker is. Let's go now and let's define this thing called, and I'm going to call it sum of squared errors. The book, ISLR, calls it the residual sum of squares, right? Page 69. You can go back and check that out. But it's just simply the so here, let me put it in blue here. SSE is equal to so let's just get the formula here. I equals to 1 to n, because I have n data points, and I'm just going to use the same notation we've been using in class, yi minus y hat, right? So the line where the data appears on the line versus whatever y is, we're going to square that sucker, and that's what's going to be called the sum of squared errors. Okay, so we'll talk about what the sum of squared, I kind of wrote it out already down here, but what it really is kind of telling you. And we're going to need that idea here in a second, but that's the formula, right? So what am I trying to do here? I'm just basically trying to figure out, well, how far away is that one? How far away is that one? How far away is that one? And so on and so forth. And we're squaring it, not taking the square root. Just square each one of them, and it gives you a semblance of how far away they are from where we expect them to be, right? I expect them to be on that line. I expect that sucker to be on that line. Why? Because remember, epsilon was equal to 0, the expected value. So we expected that sucker to be on the line. But because sigma squared is in there, there's a variance in there, it's not necessarily going to end up on that line. So that's what we're doing here. We're estimating this. We're using this SSE, this idea of sum of squared errors, to estimate how far away these things are from the line. And so, if that's the case, then I can make an idea of what this sigma is. And again, because we're estimating it, just like we did beta 0 and beta 1, when I'm estimating something using the data, I'm going to put a little hat on there. So I get sigma squared hat is equal to, I'm going to let it be SSE divided by n minus 2. And we can write it this way too. If you guys are super, you want to actually see the formula there, y hat I squared over n minus 2. Actually, I probably should, let me do this. Let me put this in here just to remember, right? So what is y hat? Y hat is beta 0 hat plus beta 1 hat times x1, 1, right? So you put the data point in there, and I'm going to change this to a bracket, right? So we actually put the data point each. Remember that is the predictor, right? So I'm talking about the first predictor, and I'm only using one predictor in this particular scenario, and that actually should be I, and then we're going to square it. And let me put a parenthesis around there. Okay, so if you put each one of the data points, right? So this would be x1, 1. This one would be x1, 2, ... all the way, that would be x1n, right? I'm using the same notation that we have in class, where that is the predictor and that is the data point that we're on, right? So that would be the first data point, the second data point, and so on and so forth. Okay, there's a reason why I rewrote that instead of y hat. So that is the same thing as that, but I guess the reason why I wrote that out is because I wanted to explain this n minus 2, right? So I haven't talked about that. So there was an n minus 1 over here, and it's the same reason that we use n minus 1 over here. Is we use the data one time to figure out what that parameter is in order to do this calculation, and in this case we used the data already to find these two things, right? So there's two parameters that we found an estimate for, and we used those two parameters in this estimate. So we have n minus 2 degrees of freedom, n being the number of data points that we have. Okay, just wanted to make sure that you guys got that. So I can write it out here just so you have it here. So because the data is used to calculate, was it beta 0 hat, and beta 1 hat. Okay, so we got that going for us. Now we come down, and so now what I want to do is, instead of just looking at the formula for SSE, let's think about what really SSE is doing. Let me choose a color here. So a measure of how much variation that cannot be explained by the model, right? So regardless of what we do in this picture here, there's going to be, so if we knew the true value, there's going to be some randomness in this model, right? Because remember, it was y equals to, so remember what the model was. So it was y, if we even knew the true parameter, beta 0 plus beta 1, x1, and then plus some epsilon, right? So we don't know, well, we don't know what these parameters are, but even if we did, it wouldn't matter, because there's gonna be some randomness, and it depends on how big. So where epsilon is that normal 0 sigma squared, it just depends on how big that sucker is. And what we're trying to do up here is get an estimate for how large that thing is. But really, it's that variation that we cannot, nothing we can do is going to be able to explain that variation. So let's just go ahead and say that that's the variation that cannot be explained by the model. Okay. And then you can read down here, it talks about the true value sigma squared is large, and the random of the process, the randomness of the process cannot be explained by the predictors, right? So that's the idea. And then the last part here is this is a measure of the so SST. So I haven't really talked about SST yet. It's in page 70 of ISLR. But what we're trying to do with SST is get an overall measure of the total amount of variation that's in the response. And I kind of talked about this, or when I said normalize, I kind of talked about this earlier, right? So if this is in billions, right? If my scale is that's 1 billion, 2 billion, 3 billion, 4 billion, 5 billion, 6 billion. That's totally different than if this were 1, 2, 3, 4, 5, right? So the amount of variation that's in this response is huge if it were billions versus if it were just ones. So what SST is measuring is how much variation is in that response variable, right? So that's what SST, the total amount of variation that's in the response. That's all we really care about for SST. And let's write down the formula for it. I don't know. Let's just put it in white. I don't know. I like that peach color. Where'd it go? So we'll put it in peach. And what we'll say is that it's just, all you're doing is just adding up I equals 1 to n of yi minus y bar squared, right? So that's that SST. Okay, so let's go down. So I got the so, right? There's always a so what, right? If I know what SSE is, if I know what SST is, those are two measures. The one thing that I haven't talked about yet is the amount of variation that is explained by the model. But the deal is, from the total amount. So here, let's just write this down. So the total amount, SST, right? Variation is either explained or not explained. So there's no other bin for it to fit in. So if I have SSE plus the variation that is explained, variation that is explained by the model, then if I add these, so let me matter of fact, I'm gonna write this here. I write it in this color because I think I used blue up here, right? So SSE is the variation not explained by the model. So the idea here is that so all of this variation is either in one of these two buckets. It's either explained by the model or it's not explained by the model. And really that's all you got to understand, right? So that, I mean, it's a 0-1 kind of thing. It either is or isn't. And if that's the case, then we can make this sort of conclusion that the variation explained by the model is simply equal to, so check it out. So it's this piece right here. All I'm gonna do is take this piece and move it on the other side. So I have two calculations that I can actually do. It's just equal to SST minus SSE. So again, two calculations that I can actually do, and I get a semblance of how much variation we are explaining. Okay, so if that's the case, then I feel pretty comfortable with the rest, right? So if I want to now find a measure. So remember, well, I want to be able to compare models. That was the idea of this video. I haven't really talked about it yet, but we're about to right now. So if I'm comparing models, what I want to do is I want to find this thing called, it depends, I guess it depends on what the book, I think they all use coefficient determination. And we use that to compare, not even just two models, even just compare models, right? So compare multiple or any model. What you want to do is you want to say, well, what we want to do is we want to find out what the proportion of the total variation explained by the model that's attributed by that linear relationship. So the proportion of the total variation explained by the model. So if I just understand here, let me underline that. If I just understand this, the proportion of the total variation that is explained by the model. That's a pretty simple idea. So I can now write the equation for that, right? Because I want, let me just write it out in simple terms, right? So I'm going to take these words and turn it into, so the proportion, right? So that means it's a fraction. So the variation explained by the model. Yeah. The model divided by what? The proportion of the total variation. Where what is total variation? That's SST, right? So total variation. Okay, and we've already talked about both of these, right? So if we just kind of come up here and look, they vary explained by the model, SST minus SSE, so it's SST minus SSE, all divided by, the total variation that we've already talked about, SST. Then we have I can put numbers into all these, and it's just equal to 1 minus. So I think this is the formula that most people see, right? So you just take SST and put it underneath that, take it underneath that, just simple fraction stuff, and you get that. Okay. That's really all I wanted to say about this this lesson. So hopefully this wasn't too long. R squared is something that we're going to use. You've seen it before. I know everyone in here has seen it before. It's just simply this idea that I underlined here in peach. This idea of the total variation explained, or the proportion of the total variation that is explained by the model. All right, that's all I got. Hopefully you guys got something out of this, and we'll see you next time.